Hello, everyone, and welcome to the Armstrong Fluid Technology webinar series. We appreciate your time today. My name is Neil Martin, Regional Marketing Manager at Armstrong. Armstrong Fluid Technology is a global leader in providing the building industry with fluid flow, energy transfer, demand-based automation, and fire safety solutions. The title of our webinar today is a comparison between variable primary flow and primary-secondary chilled water systems. Our Armstrong Commercial Building Performance Expert and presenter is Peter Wolf. Peter is our Business Development Manager with more than 36 years experience in the commercial HVAC industry. We're also pleased to have with us today Laurent Chevalier, one of our building HVAC systems experts who will join us during the Q&A session. We would like to say welcome to building owners, consulting engineers, wholesale and sales rep partners, contractors, and Armstrong employees attending our webinar session today. We will have a Q&A session immediately following the presentation. To participate, please type your question in the question section of your GoToWebinar control panel. We're all working remotely and we'll do our very best to deliver an exceptional virtual event experience for you today. I would like to now hand the session over to Peter.
Thank you very much, Neil, and thanks everybody. I want to thank you all for joining, and I hope this presentation will be informative and enjoyable, if not entertaining. Over the last several decades, Armstrong's innovations, driven by the top three competencies here, demand, heat transfer, heat exchangers, fluid flow, pumps and valves, added to which demand-based controls capability, they've enabled Armstrong to develop smart mechanical products such as our sensorless design envelope variable speed pumps, variable speed design envelope booster sets, and heat transfer packages that enable the buildings they serve to be easier to install, set up, and operate, while reducing operating costs and the quantity of CO2 emitted into the atmosphere. And we've been working for the last decade on digitalization. How did that come about? Well, in our workings with owners and managers, we saw that system problems go unnoticed for a long time and deprived the building from realizing the benefit of our technology. These challenges caused a downward drift in plant effectiveness and efficiency, wasting lots of energy. We knew that we could empower our products to address these issues in real time through the life cycle of the plant using our fourth core competency, digitalization. This creates new value for installed Armstrong products and provides optimum performance over the whole lifetime through active performance management. So today's talk on pumping systems, it follows on from the webinar given by Zelco a few months back. This time, we're going to take a deeper dive into the sequencing of the controls of the two methods and how they compare in terms of efficiency, effectiveness, ease of operation, and of operability over the long term. Many thanks to Roy Hubbard, whose work in this subject provided the bedrock for what you'll be seeing. Now, before we get into this, to help us understand better the system slides, it's best that we remind ourselves that the cooling load of a system is equal to the flow rate of water through that system times the delta T, the rise or the fall in temperature. This is the most important formula to know because if at a constant load, if the delta T is reduced, then the flow rate must go up to compensate for that cooling load. Or if the delta T goes down, then the flow rate must go up. If the delta T goes up, the flow rate must go down. We'll be coming across this when we get into slides later on. The other piece to remember or to know about is that constant speed chillers efficiencies have a different curve than variable speed chillers. And by curve, I mean efficiency curve between loading of the chiller and its efficiency here. You can see here that on a constant speed chiller, it's most efficient with the lowest amount of kilowatt needed for every ton of cooling provided at full load. And that as you unload the chiller, the efficiency goes down. It requires more kilowatt in order for every ton of chilling. Whereas a variable speed chiller has the same efficiency at full load as the constant speed chiller, but as the load reduces on the chiller, the efficiency goes up. The amount of kilowatt required of power input to generate that ton of cooling goes down. Then more or less a variable speed chiller will be at its most efficient at slightly under half load, maybe about 40%. So armed with this information, And one more thing, we'll get into the chiller pump slides. And the other thing to point out is that the efficiency of the chiller also depends upon the temperature, the entering condenser water chiller, entering condenser water into the evaporator from the cooling tower. This black line here is the typical 85 °F entering cooling water temperature, which is in many parts a default number. But if you reduce that number, then the chiller becomes significantly more efficient. So we'll be looking at that as well and talking about that in the slides showing the control of chiller plant. So let's kick off with the constant primary variable secondary type circuit. It's a very common system. It's used particularly in large central plants such as district cooling plants or college campuses or hospitals. It has two chill water loops, here and here. Constant flow primary loop that maintains constant flow through constant speed pumps through constant speed chillers. It has pumped by smaller low head pumps, which are just pumping through the heat exchanger in the evaporator, and then through the mixing header, or should I say the loop mixing header here in the mechanical room. The second set of pumps is the secondary chill water pumps. They will be taking water from the mixing header, from the chiller, and pumping through the system, through the control valves here, which are controlled by the building automation system, and they're controlling the flow through into these air handling units, which are taking the cold water and then with fans behind them are pushing cooler air into the zones. And then the water going through the coils in the air handling units pick up the heat and return back to the chillers at a higher temperature. The previous slide here showed dedicated pumps for the chillers. They're often used if you have different sized chillers so that you can have pumps sized to match each chiller so that you get the right flow through each chiller all the time. The alternative is to have headed pumps. Those work best with identical sized chillers, and the benefit here is you have greater redundancy because any one pump can handle any of these three chillers shown here. The bypass loop, or should I say the bypass loop, the mixing header, it's got to be big enough and long enough so that the warm water here doesn't find its way back into the cold water here, and it's got to be large bore enough so that the pressure loss from one end to the other is very low, so that the water just once again isn't pulled through or pushed through from this end here. Oh, the other thing to mention, of course, is that the primary flow must always be more than the secondary flow. The water in the header here must always be going in this direction, down, rather than that way up here. If the flow rate in the secondary circuit is more than the flow rate in the primary circuit, the warm water will come back in here and go back into the building, causing the system to spiral out of control with excessive numbers of chillers and cooling towers working for the actual load itself. So that's one point to know. Primary flow must always be equal to or greater than the secondary flow. So let's put some numbers to our design and operate the system at varying loads and see how the units how the chillers and pumps are sequenced in and out. At design, 100%, we have three pumps, each at 1000 GPM, dedicated, pumping through the three 500-ton chillers, which cool the water from 56 degrees coming back from the building down to 44 degrees going back into the building. These pumps are generally low head pumps. Say, for example, these will be about 50 horsepower, whereas these ones here will be high head pumps pumping longer distances right through to the far end of the building, through the coils and the control valves, and will require generally about 100 foot of head. Secondary pumps are sized for 50% duty, 50%, and then 50% standby. In this particular case, two pumps running at 1500 gallons a minute at full flow will then take the 3000 gallons a minute out of the primary side and pump it through the secondary side through the air handling units, where they're warmed up and back to the system. Because there's 3000 here and 3000 there, there's nothing going through the mixing header here. And at 3000, of course, at full load, the chillers are operating at peak efficiency because they're constant speed chillers. Let's go to 75%, 3/4 load. We'll continue to have the 3 primary dedicated pumps pumping through the chillers at 1000 gallons a minute each. As the system is now got a 75% load, we'll now only be needing 3/4 of 3000, 2250, which will be dividing between each of the 2 pumps at 1125 GPM. Control valves here will have throttled down on the flow because the building management system says they don't need so much cooling going into the rooms, into the zone served. The temperature will come back here at 56 degrees, maintaining a 12-degree delta T across these zones. But with 3000 going through the primary circuit, 2250 through the secondary, you'll get 750 going through the mixing header here, mixing with the 56-degree water coming back, cooling it down so that it's at 53, going back into the chillers, resulting in a 9-degree delta T across the chiller. So the chiller will be unloaded to 375 ton from its 500 ton capacity. And because they're constant speed chillers, the efficiency will be degraded somewhat. Let's look at half load. Using load-based sequencing, we turn off 1 chiller. And now we have 2 1000 GPM dedicated pumps that throw through 2 500 ton chillers, both 3/4 loaded, cooling that water from 53 to 44 for a 9-degree delta T. In the secondary pumps, which are variable speed, of course, slow to 50% of flow, so that there's only, and we take out 1 pump, so there's 1 pump running at 1500 gallons a minute that flows to the coils, warming that water from 54 to 56, maintaining a 12-degree delta T across the zones here. And then the bypass line will have the difference between the primary and the secondary, which is 500 gallons a minute, pumping through the mixing header, mixing with the return water, heating it up to 53 Fahrenheit. So once again, we have that 9-degree delta T with the chillers working off their peak efficiency. At a 1/4 load, still using load-based sequence, we now turn off 2 chillers. We now have 1 1000 GPM primary pump, cooling that water from 53 to 44. In the secondary loop, secondary pump slowed to 25% of flow, or 750 gallons a minute on 1 of the pumps through that zone here, 56 in, 44 out. We have 750 in the secondary, 1000 in the primary, so you've guessed it, we have 250 in the bypass, mixing with the 750 coming back to produce this mixed 53-degree return temperature, a 9-degree delta T, and once again the chillers operating off best efficiency at 75. The 1 chiller working at 75% loading. So that's a constant primary, variable secondary, how the pumps and the pumps and the chillers are sequenced in and out on the primary side, and how the secondary pumps are sequenced in on the secondary side. The number of pumps working on the secondary side have no bearing about what's happening here on the primary side. Let's look and see how variable primary flow works. Now in this case, we've got, as before, we have a choice between a dedicated system here where pumps are dedicated for each chiller. We will be looking at headed shortly, but what you'll notice first is that there's just 1 set of pumps circulating water through the chillers and all the way around the building to the air handling units or fan coils or chill beams before it comes back again. The pumps, as in the secondary chilled water pumps and previously, the pumps are controlled to maintain a constant differential pressure at the remote load, either by using the traditional method of having transducers connected to the BMS, wired all the way back to the mechanical room at great cost, or by using sensorless control. At periods of, now, the thing to note here on a variable primary is that at periods of very low demand and consequently low flow, the controls will be set to open up this valve here in the bypass line. This bypass line valve is normally shut, but in the case, it will open when the flow rate drops to a very low number below the minimum flow stated for a chiller, at where the chiller would otherwise go into a low temperature cutout. So you need to have a flow meter, and here in the mechanical room, connected to the building management system, ready to open up this valve at a drop of a hat, thus providing minimum flow through the chillers and preventing low temperature cutout. Now, by the way, as we'll see in the forthcoming slides, all these controls functions are available in Armstrong's design envelope technology, reducing the building automation system scope of supply, the cost, and simplifying the install. Right. The alternative, of course, is headed pumps. What you're seeing now is the same as before, except the pumps are now headed together and will be operating in parallel. This provides greater redundancy. If any one pump goes down, any of the other two pumps can handle any of the three chillers showing there. So let's look at the full load picture for variable primary flow and put some numbers to our design, and we'll operate the system at varying loads. A design will have three 1,000 gallon a minute pumps. They're no longer sized for 100 foot or 150 or 50 feet. They're sized for 140 foot of head, which is less than the sum of the heads of the primary and the secondary. The reason why is that there isn't a second set of pumps or pumps valves, and you take out their resistance out of the equation, resulting in a lower foot of head for the primary pumps, which will help then reduce the power absorbed of this primary variable primary system. They'll be pumping through 500-ton chillers and producing. The chillers will be controlled to produce a 44-degree leaving chill water temperature, passing through the air coils in the air handlers, where they'll accept heat from the zones being served, which will warm the water up to 56 degrees Fahrenheit and then return back into the chillers. As long as the minimum flows to the chillers are not breached, the bypass valve remains closed during normal operation. The three-quarter load will have the three main pumps will be slowed down from 1,000 gallons a minute to 750 gallons a minute, producing 2250 GPM in total. That'll go through the coils once again entering at 44, leaving at 56, 12-degree delta T, and that delta T remains the same across the chillers. So that in this case then, we've got the same delta T, but a reduced flow across the chillers, compared to the primary secondary, where we had a reduced delta T and a constant flow rate through the chillers. The bypass line remains shut as before. Moving down to half load. Now here we're provided with some options. We can continue to run all three pumps or shut one off. We can run just all three chillers, or we can shut one down. We could run 3 pumps and 2 chillers since the piping is headed. This is where chiller plant optimization comes in to decide which is more energy efficient. Chiller plant optimization is provided by Armstrong's Optivisor system on a retrofit basis, and our IPC 11550 for new build projects. For this example, we've opted for energy-based sequencing as opposed to load-based sequencing, as these are variable speed chillers, which will now be running more efficiently at half load. So we have the 2 pumps slowed to 75% of flow through the 3 chillers, each 50% loaded, cooling water from 56 down to 44, and running at 75% loaded, their efficiencies improved compared to what they were at full load. If we take it a step further and go to, there's us with the chiller off, and we go to the 25%. We'll do that after we have a little look at the staging of the parallel pumps. We've taken for granted that we've got parallel pumps in operation here using headed pumps. What we want to talk about now is how we control them. The traditional way of controlling pumps is by staging in extra pumps on demand at maximum when they approach maximum speed, and staging them out when demand is dropping at minimum speed. The challenge with speed-based staging is that you're running the pumps through a large part of their operating load, both at low efficiency and high efficiency. Armstrong developed a few years back and patented the best efficiency staging method. We program in, we know the performance of the pumps, we program in the maps and the best efficiency point of the pumps, so that at this point here in the operating spectrum, rather than have one pump running approaching its maximum speed, we'll already have engaged the second pump, and we're back onto best efficiency with two pumps running, absorbing less power here than we have with a single pump running. Armstrong is the only company that has parallel sensorless pump control embedded into its design envelope pump controller X Factory, available for enabling whenever it's so ordered. And it looks like this is what the design envelope pump controller looks like, offering a screen that resembles that of a large screen type iPhone like the XR. Easy to read and operate. So let's go back to this 25% of quarter load scenario and see how that pans out. So this is what makes variable primary so optimizable and versatile as well in terms of what decisions we make. And we can really save a lot of power here. We could continue to run all three pumps or just shut one or two off. We can continue to run all three chillers, or we can just shut one or two off. The list goes on. For this example, we've continued to, we're looking at load-based sequencing, which is not the most efficient way of working. We've taken out two chillers, and we've got one chiller working at 3/4 load. So it's operating at a little bit better efficiency than it would have done at full load, but we could have made it even more efficient by just having two chillers together at 37.5% each, and that would have optimized the efficiency better, assuming that there was a full chiller plant optimization in place. So we have a total of 750 GPM passing through the coils, and the chillers once again run to that fixed delta T of 44 out, 56 coming back. The last off-design point we want to look at is when minimum flow is reached through the last chiller. This occurs when the system flow goes too low to keep the chillers from freezing. In this example, for example, the minimum flow for the chillers is 250 gallons a minute, but the coils are unloaded to 100 gallons a minute. As soon as the system flow, as measured by a flow meter, in many cases the Armstrong design envelope pump, which measures flow and can communicate that number to a building management system, as soon as the flow is measured drops below 250 GPM, the building controls will open up this bypass line here. So it'll be open, and you'll be getting 150 gallons a minute going through the bypass, 100 gallons a minute through the load, a total of 250 gallons a minute, safeguarding the chiller here and preventing it from freezing up. During this operation, the newly created loop around the chillers and pumps becomes constant flow, and the new loop here between the bypass and the load is a variable flow, which kind of sounds like the constant flow, variable flow system we were looking at originally. But this only applies in bypass mode. Once the load goes up, once the valves open up and the cooling load increases, the valves open up, the controls will open up, will close the bypass, and then allow extra flow through the system, and it's back to normal again as a variable primary flow. So by looking at the bypass and learning how the chillers can freeze up under certain circumstances, we're now going to address some of the challenges that variable primary flow provides. The reason why it's variable primary flow as a technology is relatively recent is because chillers weren't capable of handling variable flow through them until the last 10 or 20 years. Better chiller controls has improved the situation sufficiently for chillers to handle variable flow, but flow still can't be varied too quickly or they will trip out on low water temperature. How fast is too fast depends upon this list of items here. The most important of which have very little to do with the chiller themselves. A centrifugal chiller, for example, may handle flow rate changes of 30% per minute in one system, yet for another system, it can only handle 5% per minute in yet another. Yeah, it's the same chiller. The maximum rate of change the chiller can accept is dependent upon the type of chiller. Centrifugal chillers are relatively fast. Absorption type chillers are very, very slow. The key thing is that the load of chiller, and the key thing is the rate of change of chiller, sorry, the rate of change of load at loading. If you have a lot, chillers can accept a faster rate of change when they're fully loaded than they can when at low load, where they can accept almost no change whatsoever. The other key issue, or key determinant, which is not really in the hands of the designer, is the amount of water in the system. The more water there is, the more thermal capacitance, the more it will dilute the effect of a change of load, thus allowing a fast change of load if you've got a lot of water in the system. Similarly, if the load is far away from the plant, by the time it gets back to the chillers, the change will have been slowed down. So what you have to do at commissioning in order to ensure that you don't result with the chillers tripping out on low temperature is to make sure that the controls are slowed down. Here we have the pumps will have their speed controls set so that they speed up by no more than 10% a minute. So they'll start and stop over a 10-minute period. Similarly, the flow control valves on the air handling units will be set with a very large cycle time between fully open and fully shut. So let's look and see how this plays out in practice with regard to the rate of change and how the chillers are operated. Say we have during normal operation at low load, just one chiller working, and the load is going up. The chill water return temperature is getting higher than 56, and so the chillers need to. This chiller is at maximum load, and we need to bring in another chiller in order to keep the chill water supply temperature down at 44. So you'd think, well, to do that, the first thing to do to open up a chiller is to open a control valve of this chiller here. We do that. If we open the standard control valve, which opens and shuts in about 10 or 15 seconds, what's going to happen? Well, the chiller that is operating will see the flow rate through it dropping by half, because the other half will be going through this chiller, which is about to start up. The problem is that the chiller here has got its capability to deliver cooling depends upon the inlet vanes on the compressor, and they take about 2 minutes to go from fully open to fully closed. Therefore, if the flow rate is going to drop by 50%, you'll need about 90 seconds for the chiller to respond to that halving in load. But if the valve opens in 10 or 15 seconds, then that isn't going to happen. Instead, you'll end up with half the flow rate, but the same amount of cooling. So with half the flow rate, the same amount of cooling, you get the delta T, the drop in temperature is going to go from 12 degrees to 24 degrees. So the return temperature is going to drop from 56 less 24 down to 32 degrees centigrade, freezing. As it happens, the low water temperature cutout will kick the chiller off once it hits 40 degrees Fahrenheit on those systems. So you end up with the chiller tripping out when you're trying to start a chiller, which is not a good thing. The solution is to use a valve here which modulates to open slowly over 1.5 to 2 minutes, so that the inlet vanes on the chiller compressors can keep up and start the second chiller without a hitch. So we've looked at some of the challenges involved with variable primary flow. You need to make sure that the chiller control valves operate slowly, the speed controls speed up and slow down pumps slowly so that the chillers can catch up. Let's have a look at some control equipment that Armstrong has sold into places in the marketplace, and we'll look at some case studies after this. But let's look at the 4500 first, the IPS 4500. It's specified for a variable primary application. It controls the primary pumps, and will always be aware of the minimum and maximum flow rate required by knowing the number of chillers in operation. It will control the bypass valve to ensure the flow rate required by the number of chillers in operation is met. It's programmed to ramp the pumps to maximum speed when it learns of another chiller starting or chiller isolating valve opening up, just to make sure there is enough water flowing through the chillers to prevent low water temperature cutout. The 4500s can be specified for applications using up to 8 pumps, 16 zones, and 8 chillers. Let's have a look then at the IPS 4000, which is specified for variable secondary applications. It stages them in and out on best efficiency basis as per the 4500 and works on the information provided by the sensorless pumps, which tell them the flow rate. It's embedded sensorless map, and it's got an embedded pressure control curve that emulates the response driven by a remote mounted transducer. But the IPS 4000, like the 4500, can also work with pressure and/or temperature transducers and operate using sensorless as well in hybrid mode, where the transducer takes precedence. Say, for example, it's managing cooling water flow to a server room with the transducer there. That will take precedence and ensure the server gets the cooling all the time. Again, these features are just not available from other manufacturers. The IPC 9521 is the only chiller plant automation device available as a configurable product. It controls the primary pumps, it controls the condenser pump speeds, it controls the speed of the tower fans, it stages the chillers on and off according to the load, and it manages the chill water supply temperature and the entering condenser water temperature from the cooling towers. And it'll open up the bypass valve at minimum flow. It uses the GPM numbers that the sensorless pumps communicate to it, and it handles any transient conditions as we discussed earlier. It can also manage unequal sized chillers, so you can have a pony chiller and full size chillers. Total of 5 pumps, 5 chillers, and 5 towers can be controlled by 9521. Let's look at some of the case studies. Here's an IPC 9521 chiller plant control system. It's located in Moncton, New Brunswick, Canada. This organogram is one of the largest cannabis growers in eastern Canada. With a custom designed HVAC plant like this, the organogram aims to meet the medical and recreational needs with its recent legalization in Canada. The plant is one of the largest cooling projects in Moncton and one of the most unique ones with the need for heating and cooling using both heat recovery chillers and normal chillers. It uses a combination of heat recovery chillers to pre-cool the chill water return and then take waste heat from it for heating purposes. And the main chillers take the relay baton to complete the rest of the cooling. We've provided our design envelope IFMS, prefabricated pumping systems for the chiller plant, 2 customized IPC 9521s offering chiller plant automation and optimization to work with this unique configuration. A more conventional way of getting high is to go to the 41st story, the 41st floor of the First Canadian Centre in downtown Calgary, Alberta. It was built in 1982 as over 500,000 square foot of space, and at the time it was the tallest building in Calgary when it was built. Armstrong initially installed a design envelope pump in 2016 as part of an energy upgrade project, and then in 2019 2 further new design envelope pumps were added to the system, and the 2016 pump was upgraded to the latest generation 5 with its design envelope pump controller, all connected and automated by an IPS 4500, which provides intelligent multi-zone control, integrates with the BAS, delivers optimal energy performance, and stages them according to best efficiency. And those are 125 horsepower units, 3 of them. So to summarize summarize where we've took our discussion and draw some conclusions. So constant primary, variable secondary. Primarily it's easy to establish, set up, control, and commission. The loops are separate, so it's easy to say I separate off a loop to do any troubleshooting, and you can also configure the unit, configure the system so that you can tailor the pumping systems and the circuits to suit special applications, loads with a much higher pumping head pressure or a different loading capability, knowing that the flexibility will allow the whole system to operate successfully. The downsides of constant primary, variable secondary is that it does have more energy costs than a variable primary pump system. Also, likely if it's using constant speed chillers, more chill water energy, because the chillers will be operating at part load at reduced efficiency compared to variable speed chillers running at higher efficiency at part load. It costs more because you've got more pumps, you need more plant space for it, and it's more susceptible to low delta T syndrome. This is when the secondary pumps outrace the primary pumps and pump warm water back into the zones, and then the chillers start up and the towers to catch up, which wastes a lot of chiller power and towers as well. So those are the downsides of constant primary, variable secondary. Variable primary, with fewer pumps, it's less expensive, roughly about 5% less in total cost than a primary secondary system. It requires less space because and less equipment because there's fewer pumps, and it draws less power because because of the fewer pumps, the chillers working at part load are more efficient, and you can get some good energy-based sequencing, and it lends itself to chiller plant optimization. The downsides of variable primary flow: you need to have a robust and sophisticated control system. We talked about all the ups and downs of the controls, the valves, the bypass valve, the chiller valves, and the load valves as well. And the staff operating it need to be arguably a higher skill level than those for a primary secondary. And to get the valve settings correct, you need to spend a little bit longer commissioning the system. So just getting back to the points to look out for on variable primary flow, let's keep you can have dedicated pumps with unequal sized chillers or equal chillers with headed pumps. You need to respect and know the minimum flow through the chiller so that you've got your bypass line correctly sorted out. With pumps, design envelope pumps give you that flow meter capability, which then helps to manage the chiller bypass valve operation. The speed ramping up and ramping down times for the pumps need to be set slow to match the performance of the chillers, and the chillers themselves are staged in and out based on their stage in, based on supply temperature, staged out on their load. So what happens if an engineer or an owner asks you which type to use? Well, they both have an application, so we're not going to denigrate either side. They both have their strengths and weaknesses. Variable primary flow are suitable for either a single building or a few closely sited buildings of similar size, where load variation is not going to be extreme, and where highest efficiency is required, and whether you know that they're going to have a good quality maintenance team at the back of them. Constant primary, variable secondary is best for big systems, wide-ranging systems across a large campus, be it hospitals, colleges, universities, military bases. They're going to be where you have diverse loads that can come on at different times and change dramatically. So that's where you want constant primary, variable secondary. Armstrong's range of control products extends from starting at our design envelope pumps with the design envelope pump controller, which provides sensorless speed control and also can open and shut bypass valves and simple single chiller installations. We've talked about the IPS 4000 in depth, the 9521 for water-cooled chiller plant. The IPC 9511 is for air-cooled chillers. The ITC 9521 is for systems with cooling towers, where the cooling tower is the main cooling source of supply. Say, for example, for water source heat pumps. We do the Tower Max upgrade from the IPC 9521, which will then operate the cooling tower, fans and pumps in an optimized way to minimize the power absorbed by the chiller and maximize the amount of cooling that the towers can provide. Evercool is our mission critical controller for a data center chiller plant. Optimizer and IPC 11550 are our patented algorithm chill water optimization plant, and OptiPoint is going to be our next release, which is a chiller optimization plant that uses machine learning in order to develop the lowest energy costs for a particular chiller system. That's summarizing it. So in which case, Neil, I hand over to you for questions. Thank you, everybody. Any questions? Thank you very much, ladies and gentlemen of the audience. We've talked through variable primary, and we've compared it with constant primary variable secondary, and looked at applications and how they sequence them in and out. Let's see, have we a question from the audience? What do you say, Neil?
Thank you, Peter, for that truly in-depth comparison between variable primary flow and primary secondary chill water systems. We would like to now open up the sessions for question. Again, to ask our panel of subject matter experts a question, type your question in the question section of your GoToWebinar control panel. Peter, we have a number of questions already for you and all Laurence. The first question, we usually like to have our BMS control the pumps, the chillers, the valves, etc. We still have to control the remaining systems in the building. If we use Armstrong IPS controls, then it becomes difficult to mix and match. What would you recommend here?
Actually, let me take that one.
I'll
give you a break. I'll give you a break. No, actually, no. It's really easy. The first thing is to plan the point that will be taken care by one of our control system, and the one that will be left to the BMS, which is really easy to plan from the design. We have available the list of points, input, output, that the BMS will know in advance that the IPS or the IPC will be controlling. And then after, all our control system communicate with our standard communication protocol, BACnet, MSTP, Modbus, BACnet, MSTP, BACnet IP, and those point lists, something are available and ready to be used by the BMS. So yeah, so in a nutshell, we are totally transparent. So it's easy to plan ahead, easy to install, and easy to communicate. And the advantage that it will give is that we will provide that portion and expertise that we have to control and optimize the system, whether it's just the pumping system or the full chiller plant, and leave the BMS have a view, completely transparent view of what we are doing and what we are providing, and that way we are a perfect complementary to the BMS.
Yeah, I just say it'll integrate. It'll integrate it. I think that there is a tendency there to think of these things as some sort of black box, and it ain't. It is not. It's something that's very easy, that is totally integratable with an existing BAS.
And another advantage, since I got on it, sorry, is that we can, because it's pre-programmed and pre-engineered and pre-tested, it's easy and ready to install at the same time of the equipment. So compared to a BMS, which will have a bit of delay when it's about to be installed, let's say few weeks until the control team arrive it. Here you can save some time and run the plant way before the equipment way before the full plant is commissioned. So it's another advantage that the BMS will definitely have an advantage on.
Yeah, and we've worked with our PS 4000 for over a decade, and it was derived from earlier controllers that we've had before that, 3000 and the like. So we've got a lot of experience of working with building automation systems.
Thank you, Laurence. Thank you, Peter. The next question for you, is it easy to upgrade a constant primary variable secondary to variable primary chill plant? And what are the benefits and estimated energy savings when you do that?
Interesting one, that. I don't think I've seen that happen, frankly. To do that, you need to make sure that the chillers are suitable for are the chillers variable speed chillers or not, would be the first question I'd ask. And it's likely that if it's a conventional system, then they're constant speed chillers. And if they're constant speed chillers, then the first thing you've got to do is look at your chillers and convert them to variable speed, and that's a fairly significant work in itself. So I'd say that to me, I'd hesitate before looking at converting constant primary variable secondary to variable primary only. If you could do it, then yes, you get the efficiencies due to the fact that variable speed chillers are more efficient than constant speed chillers at part load, and you've got a little bit less pumping power as well. So you'd and then if you could apply chiller plant optimization to the whole of it, then yes, overall you'd be looking for, I don't want to pluck a number out of the air, but it would be upwards of 10, 15, approaching 20% savings on overall power. And Laurence, am I being overly conservative?
Yeah, but it depends what you're doing. My main recommendation would be to you won't be able to get rid of the secondary right away. So my main recommendation would be to jump from a constant primary to a variable. Sorry, constant primary, yeah, to variable primary, and then we can skip in the background the variable secondary. So that way, as you said, upgrading the chiller definitely from constant to variable, you can jump easily and get even more, 50%, 60%, just doing that. And then we can keep in the control, we can keep that secondary actually in the background and definitely optimize the overall. That's definitely an interesting one, and we can run an energy analysis actually to run that scenario and definitely recommend a solution to optimize and the quantity of savings. And then obviously it would depend on the size of the chillers, the capacity, the location where you are. But definitely it's an easy one we do that every day to estimate that energy savings.
So you're looking at going from constant primary variable secondary to variable primary variable secondary. Okay.
Correct. I would do that because the secondary is there for a reason. As you say, it might be a large campus if you have to distribute. So and then after, ultimately, it depends how far you need to do the upgrade. You can think about removing that secondary pumping system, but again, depending why they were there at first. But that means that you have to take into account in your primary pump the head that you will have now to carry to get up to the end of the system, which was actually the point of the secondary system.
Okay. Excellent. Very thorough answer. The next question for you. Can you set the ramp function in the pump control to speed up, increase flow in this case, and slow down to decrease flow?
Yes.
So that's an easy, straightforward thing to do.
Yes, you go to the DPC keypad, you press the controls, you go into, I think you do it on the Wi-Fi connection. So you connect to the pumps using the web browser, and you just set the ramp time on the web browser connection. So you can do it using your smartphone.
Excellent. Excellent. The next question. We often use variable primary on heating systems. What do you see as a difference in the system as they apply to heating boilers?
Well, it's a great question, because that's going to be, I think, a presentation I'm going to be putting together for in the near future. So for boilers, so for variable primary systems with boilers, there are some similarities in the logic. Whereas with constant speed, with a conventional boiler installation with constant speed pumps, you're working at different, you've got the boilers going on and off, you've got a variable delta T across the system, depending on the load. Whereas with variable primary boiler systems, you've got a fixed delta T and an adjustable flow rate, as opposed to a moving delta T and a constant flow rate on a conventional system. So there's a lot of similarities in the control, in the thermodynamics of it, and in the control of it, and similar issues with minimum flows and the ability of the boiler. Except generally gas-fired boilers can adjust their load quite quickly just by giving you more flame out of the burner. So they don't have those challenges. That's kind of interesting question. I think I've only covered maybe half of the salient points arising. The other challenge with chip boilers, of course, is maintaining a return temperature, especially if they're condensing boilers, to ensure that you're getting the highest efficiency with the most condensation into the heat exchanger at 130 Fahrenheit, or trying to minimize that return temperature to prevent it exceeding that temperature.
Thank you. And something to look forward to, another webinar presentation to look forward to from Peter Wolf. The next question for you: what is the maximum number of buildings that you would recommend for VPF?
Well, it's as long as a piece of string. It depends. If the buildings are all identical and close to each other, then I don't think there's any particular limit. But if it depends upon the relative sizes of the buildings and the relative distances. So I treat a bunch of buildings which are close by, all the same size, as effectively one building, and then I wouldn't have a problem. Then I don't think of VPF would have a problem. But if there's big distances and big difference in the pressures required, then that's more a constant primary, variable secondary, or variable primary, variable secondary application.
Thank you. The next question: does Armstrong offer service on the various control panels that we sell? Are they Armstrong's staff, or are they, true partner services?
Anna Ross?
Yes, definitely we offer services. It will depend on the region where you are. Definitely, the first, I would say, team in North America would be with the help of our staff, and we have, it really depends on the region. That's why it's a really generic question. Maybe we take that one, and then depending on the region of the gentleman asking the question, we can definitely get back.
Yes, we can get back directly to that attendee. The next question: do you recommend installing a hydraulic separator to the decoupling the primary and secondary pumping system? Do you recommend installing a hydraulic separator to the decoupling the primary and secondary pumping system?
Yes and no. It depends upon where the temperature, where the points are located, so that we get the right type of mixing. So we avoid mixing where we don't want mixing, and we do get mixing where we do. Is my answer to that. It depends on where the points of location are, because, like I said, on the constant primary, variable secondary, you want the warm water to come that way, and you want the cold water to come out that way, and you don't want them touching, getting close to each other. So that would depend upon what these separators look like. I know that there's available in the market prefabricated hydraulic separators, and it varies from. I'd have to see exactly what the pipework configuration looked like.
Thank you, Peter. The last and final question, we are a little bit out of time here. I have been hearing a lot about parallel sensorless pump control. Based on this sensorless pump control technology, is it always best to run 2 pumps at a minimum?
Short answer is no. It depends upon where the duty point sits at the moment in time versus the best efficiency number of the pump. If the duty is to the left of best efficiency of that pump, it doesn't make any sense to energize a second pump and then be even further to the left. So it's not a one-size-fits-all answer. You have to install. It's not always the case that 2 pumps are always better than 1. It depends on where the duty point sits relative to the efficiency of that pump.
Thank you.
So it will depend on where you select. So that's actually an important point, because when you design it, you have to think about that it would better. So it's part of the design criteria now to change your way to design, thinking that you can have actually benefit from that parallel saving by selecting on the right side.
So if you pick a smaller pump with a lower best efficiency, then you'll reach peak efficiency earlier on than you would with a bigger pump with the efficiency way out to the best efficiency point way out to the right.
Thank you both. Any last thoughts on Ron's? Then Peter, 1 minute, just letting our audience know any last thoughts on today's presentation.
Yeah, I see a lot of question and I see a lot of interest, and definitely we can help not just placing our solution, but definitely help with the design. And it looks like there is a lot of opportunity, and feel free to reach us anytime. So you have, and then we can assist with any of the question practically for your case, and hoping making a great design.
Okay. And what I'd add to that is, yes, I've seen some familiar old friends pop up on the audience. So thank you very much for joining in. I much appreciate you watching this presentation. Like Anne-Laurence said, we look forward to your questions and we'll answer them offline. We hope we've provided some education for some people who are new to the industry or have learned something. And to those that are much experienced, I hope I'll be continuing to learn from you as time goes forward. Thank you very much.
Thank you, Peter. Thank you, Laurence. Thank you all for joining. To learn more about Armstrong HVAC solutions, please visit armstrongfluidtechnology.com. A recording of this webinar will be sent to you via email, and that email will come from Armstrong Communications. Thank you for your time today, and please stay safe and in good health.
Thanks, everybody. Bye-bye. Take care.
Take care. Bye.